Okay, great. Should I start?
Yeah, stop.
So we are very excited to have
Oh.
Raju visiting us today, just today, right? Unfortunately. And I'm only reading your title for the first time, so I'll let you just jump right into it.
Okay, great.
He's been visiting us for years and years, longer than I've been alive in physics, so it's very fantastic.
That's aging me here. Okay, so yeah, I spent the summer '89 here as a student under the leadership of Jürgen Rendrup here. And
Really great.
at a great hotel in
That was,
Nash.
are you in the 1989 or?
1989, and I met you. You were working on crystal something, or
I know how to make people remember the place.
It was made an indelible impression. Let me just. So, and I watched The Grateful Dead at the Berkeley Amphitheater, so that was a great highlight. So, anyway, so what I'm going to talk about is something weird, and this is work in collaboration with Himanshu Raj. I see he's checking to join in to check that I don't say anything really stupid. So, anyway, so yeah, so I want to point out sort of something kind of remarkable which is physics in two very different scales, right? The macroscopic scales of 1 billion kilometers may intimately be related to physics that is really at very short distances within us, right? 10 to the minus 19 kilometers. So we're talking about a genuine correspondence between physics that's separated across 20 orders of magnitude. And so this is, of course, the famous black hole at the center of Messier. So it's about 1 billion solar masses. It's huge, okay? And the question is whether something about the physics of this can be learned from this physics here and vice versa, okay? So you might think this is completely insane, but my job here is to convince you that maybe it's not as insane as one might think. But if you think it's insane, that's a good start. Okay, so,
But this immediately strikes out. Are you the Q80CFT?
Ah, good. Okay, so please, Bill, come and sit. Guest of honor. Because Bill's giving me a ride later, so I have to. And may feed me even, so depending on how things go. So thanks for asking about ASCT. It's different. So this is really between QCD and Einstein gravity. Okay, so these have physical, real-world consequences. While ADS CFT, ADS is anti-de Sitter, which is not our universe, right? And CFT is CFT, so equal to 4. But there are some very specific differences that I'll point to because people have tried to do some of the things I'm talking about in the context of ADS-CFT, and I'll point to the differences. So if I don't remind you, so. And so this is sometimes called a double copy. Okay, this is not working.
If you click on the slide,
oh, I see. Okay.
and then right should be forward. It was working. I swear I tested it.
Okay, so now nothing is working. So okay. So since Himanshu is here, I'm very happy to mention that this is work based on work with him. So Himanshu is a Simons Foundation fellow with me at Stony Brook. Okay, so we're supported by Simons collaboration. And some of what I'm going to talk about, at least the parts, since he's listening, the parts that are reliable are now in these two archive publications, very recent, as you can see. And so this is really a culmination of 2.5 years of work. So we have many more papers coming out, so please stay tuned.
One per month.
Sorry?
One per month.
Well, okay, it's not necessarily guaranteed to continue. So the first thing I want to mention is that, so for someone like me and people my age or older, black holes were always like sort of these exotic solutions of general relativity that you open Chandrasekhar's book and there's this magisterial kind of exposition. But now they're kind of everyday objects we have to take seriously. Okay, so there are measurements done, and you can sort of look at physics from black hole mergers, and as evidenced by these Nobel prizes first for the discovery of gravitational waves to Rainer Weiss and Barry Barish and Kip Thorne.
You can take comfort in the fact that they're all older than you are.
Yes, they're all a little bit older. I think Rainer is still going strong, actually, and Barry's now at Stony Brook, and his son Ken Barish, I think many of you know very well. So, and of course, then of the 2020 prize, deservedly to Roger Penrose, Reinhard Genzel, and Andrea Getz, and in particular for them, for the discovery of supermassive compact objects, center of our galaxy, and as we know, in other galaxies as well. Okay. So some of my interest was motivated in discussions with Gia Dwali. And Gia has been kind of trying to understand sort of this classical picture of black holes. Really is, kind of sort of quantum, how do you think about these objects in quantum field theory, sort of in some consistent way. And so this goes under the name the black hole end portrait. And so, of course, in gravity, black holes are macroscopic objects with geometric and thermodynamic properties, as we understand. And in QFT, based on his work, our understanding of black holes is really is in this picture as really highly occupied states. So these are states of gravitons. So you can think of them as self-bound states of gravitons with extremely high occupancy. So the occupancy in gravity is the mass of a black hole squared divided by the Planck mass squared. And if you just calculate what this is for solar mass black holes, that's 10 to the 66. So it's a very good classical state because
The cookies have arrived.
The anomalous gravitational force.
okay. So this is an informal talk, so please feel free to interrupt. So this is very, very high occupancy. So when you think about, say, in quantum mechanics, what is the classical state? It's the limit of infinite occupancy, right? The quantum state. And so that's taking n to infinity, right? So that sort of h bar over n goes to 0 and so on, right? And so, so this is saying that n is very, very large. So it's a very good classical state. It's really an excellent classical state. However, it's not fully a classical state. Okay? So it has quantum corrections, which are 1 over n, and those quantum corrections are important. Okay?
I mean, this n is how many quanta per quantum state, or what is it?
Yes, this is literally the occupancy.
So
Space density.
That's how many photons will be in.
This is not number of gravitons per unit volume per unit mass.
Bosons of some sort. Right?
Sorry?
These are bosons.
Yes. Yes. So it's a self-bound, okay? And as I'm going to argue that it's a leaky bound state, and the leakiness is characterized by 1 over n. Okay. And so the way you think about this black hole is by taking the semi-classical limit, okay, where n goes to infinity and the Planck length goes to 0, in such a way that the Schwarzschild radius, which is twice g, which is Newton's constant, times this should be m sub bh. So this is the black hole mass, which can be rewritten as the Planck length times the square root of n, the occupancy, using this, right, is finite. Okay. So in this way, you can see things like how you understand things like the emergence of an event horizon, black hole thermodynamics, no-hair theorems, and so on can be understood simply in this limit. And as an example of the power of this approach, you can very simply understand how things like Hawking radiation occur, where if you think about a system where you have these n energy levels, okay, so think about a system where you have occupancy of n energy levels, and they have a slight energy separation, which is 1 over n, okay, so they're actual quantum states with 1 over n. So the limit where n goes to infinity, the separation of energy levels goes to 0, it's a pure classical state. Okay? There's no such thing, of course, in nature, but it's a very good approximation, like we are, right? And so now with 1 over n, so because you have a separation, you could just think of quanta which are kind of bound to the highest energy levels, and then you can just compute the rate of their scattering. Okay. And you just go through this nice Boltzmann expression you can recognize now with this over-occupancy factor, which is very large. And you just work out, just the simple rate equations. And you find that this is given by 1 over the Schwarzschild radius, which is twice Newton's constant times black hole mass, right? So this is the right dimensions. And this is nothing but the Hawking temperature. And then from this formula, you can multiply this by the mass on both sides, and you'll see that you get this rate equation here, the change in the mass of the black hole. It has a right minus sign. And then from this, you can calculate the black hole half-life. Okay. And that goes as n to the 3½ times the Planck length. So for 10 to the 66, you can put in numbers, it's much longer than the lifetime of our universe, right? So from the quantum perspective, these are very good classical states, even though strictly they're metastable. Okay? A black hole will decay. So you're forming some metastable state, which for all intents and purposes looks classical and stable and so on, but it's truly a quantum metastable state. That's a takeaway. Okay? And this is something called the page time. And so beyond this time, the physics becomes actually quantum. Okay? So you can also think of it as a quantum breaking time where and you'll see the analogy to the QGP as well that appears, where then at some point you have to start taking account the quantum information seriously. Okay, so let's now go back and ask ourselves in quantum field theory. Yeah, sure. Yeah.
There are many black holes. This is this was a big black hole. There are also
different sizes.
Ones,
yes. Right. Exactly. Yeah.
The smaller ones live a shorter time.
Exactly. So you could just put in the numbers, you'll see they just evaporate very, very rapidly. So people, of course, at the LFC, there was a big noise about
yeah, I was just going to mention
black holes. And actually, Gia was strongly involved with that. And also with Arkady Hamed and Dimopoulos and others. Okay, so let's think about how do you let's think of it from a kind of Gedanken point of view. So imagine you have two gravitons which are super energetic, right? So they were produced, say, right at the very start of the inflationary phase of the universe, say, they're sort of scattering of each other, Planck energies, right? And say they're producing n gravitons, right? Where n could be this very large occupancy, right? At very short impact parameters, you produce very large occupancy. You ask yourself, what's the probability to produce n? So in quantum field theory, you'll say, well, it's alpha. Well, in this case, it should be alpha gravity to the n times some n factorial, because these are bosons, right? Different combinatorics. And principle, there's some, phase-space degeneracy factor, which I'll write as e to the s. Okay? For reasons that are, the s is what you might think it is. Okay. Now, if you say, okay, let me assume that the occupancy is very large. Okay, what do we mean by very large? Right? The occupancy of a classical state is 1 over alpha. So when alpha goes to infinity, occupancy goes very, very large. So if you look at most quantum field theories, the classical limit corresponds to fields which are 1 over alpha, right? Very large occupancies when alpha is small. So now if you use Stirling's formula, okay, and then you work this out, n factorial, n to the n, e to the minus n, okay, put in n as 1 over alpha, you'll find that this is e to the minus 1 over alpha. So when alpha goes to 0, you say, the probability goes to 0, okay? So this would tell you, right, that the likelihood of forming a macroscopic quantum state with high occupancy is tiny, right? Because it's suppressed. When alpha goes to 0, this is exponentially suppressed, right? It's e to the minus infinity. And so, however, there's this factor e to the s here, right? And that tells you that if s is order 1 over alpha, right, that compensates this, and you can get probability of order 1. So if you ask yourself the question, what is the likelihood in a 2 to n process, okay, of producing a classical state, okay, which means a state of high occupancy? Naively in quantum field theory, that will be exponentially suppressed, okay, unless you had a huge degeneracy factor, right, of the entropy, the number of microstates, the log of the microstates of the system. That's why it's e to the s, right? So this is, s is log of the number of microstates, so this is the number of microstates, right? The degeneracy of microstates. And so if that's order alpha, this is order 1. And so you can understand this problem from the perspective of quantum information, which is saying that this quantum picture of a black hole, right, or this classical lump as an overoccupied state, is equivalent to saying that such states saturate the Bekenstein entropy. And what does the Bekenstein entropy bound say? That if you have, some amount of energy that you're trying to put into some fixed area in space-time, what is the maximal amount of, entropy, number of microstates that corresponds to? Is there a bound of that? That's the maximum amount of information you can put in some region in space. So if you take your brain, right, and say, okay, I have this volume there, right, and I have, so much information there, you'll find that you're very far from saturating the Bekenstein bound. Okay, maybe someday our brains will be big enough or sharp enough that that'll be the case. So if you now say that
Or small enough.
but yeah, there's
They are so tiny.
small enough, but
There's a limit of amount of information per volume.
so you say define the energy as, say, the occupancy times, so it's the times the typical energy. Let's call that QS for purposes that'll become clear. So you say that the energy in critically packed volume, right, of quanta, and then this is the same volume that you say saturates unitarity, right? And then you just work this out, you'll see that corresponds to this same value S that I got in here. Okay. So the statement is that when the same requirements in the entropy to create a macroscopic self-bound quantum state correspond to the requirement that you're saturating. And so if you now work out what alpha gravity is in terms of these units, right, of the Schwarzschild radius and the Planck length, you find that this satisfies in the area. So this is the famous Bekenstein-Hawking variable. So in this quantum picture, you see that this comes out kind of very, very nicely. And if you want to read about this, one of your colleagues here down the hill has a very nice discussion that's on the archive. Now, what about QCD? So my QS should have been a bit of a giveaway for those who are in the know here. So the way to so the question is, okay, suppose you have 2 to n now scattering, you see at very high energies, right? How do you think about it? And so the question is, when do you form a macroscopic quantum object just in scattering of 2 gluons? So if you're saying I'm going to have 2 gluons going to n gluons, right? When does that form a state? And I'm going to argue that this is when also the entropy of this object, the classical object that you form, is on the order of 1 over alpha. From the same arguments as previously, there's no difference. And so what happens is when S is of order 1 over alpha, the cross section to produce n gluons saturates unitarity and at the same time produces this classical object. Okay, so classicalization and unitarization go along hand in hand. And so the way to think about this in the usual language of perturbative QCD is that imagine that you are at some large Q squared, okay, which is reliably perturbative. And so now you start boosting this object, you start going to higher and higher energies, right? And so what you're going to have is that you're going to have more and more of these little blobs, right, at some point. And at some point, the phase space density becomes, much larger than 1. And my claim is that this is true for arbitrarily large Q squared. You could start with arbitrarily large Q squared, but then go to much higher energies, okay? And there's always an energy, right, at which you'll get maximal occupancy. My claim is that maximal occupancy is when the cross-section for that process unitarizes. And so because for each Q squared, there's a value x, or energy, for which the cross-section unitarizes, there's a line. And that line is what defines what you call a saturation scale. That's the definition fundamentally of saturation scale, is that when the cross-section becomes classical, right, you create a classical lump, right, out of a intensely quantum process, right, 2 to n scattering, and when it unitarizes at the same time. Now,
sorry, can you
yeah,
say it again?
sure.
What do you mean by the cross-section unitarization? crisis?
So when the probability becomes order 1. So naively, for a 2-to-n process, you would say it's exponentially suppressed, right? It's e to the minus 1 over alpha, right? But unless, right, the entropy goes as 1 over alpha, right? And then but that entropy going order 1 over alpha is saying that the object's becoming classical at the same time. And so what's also happening, and this is the perspective that even people who are cognoscenti, like some people in this room, right, are not necessarily familiar or maybe even more perhaps say comfortable with, is that you can think about this whole problem in the language of symmetries, okay, and Goldstone dynamics. So what's happening is, imagine that you have a 2-to-n fundamental scattering, okay, in the theory, and you form a classical lump. Okay. What are you doing? Okay, you're breaking Poincare rings, creating a macroscopic state which has a well-defined reference frame. And in the case of QCD, okay, you're also, it turns out, breaking a global subgroup of color. So the classical object is a metastable object which you create. And on the time scales of interest, essentially what you're doing is you're breaking, and I can come to that later. Okay, and this is for people who are familiar. This is what you're breaking is the large gauge transformations. And because you have broken a global symmetry by the creation of a shockwave or this lump, okay, you can think about the right degrees of freedom as the Goldstone modes of this broken symmetry, global symmetry. And in the CGC, this is a paper with Dwali, where we argued that this classical lump, which is the colored glass condensate, okay, corresponds to 1 over alpha, right, which it also satisfies an area law, except it's in terms of a Goldstone scale. So what sets a unit to that area is a Goldstone decay constant, and that's given by the occupancy times its critical packing radius, okay, with this classical lump. And so for black holes, this scale is just the Planck mass. So there's a deeper sense in which you can think of black holes as being intrinsic to gravity in the quantum field theory sense, in the sense that black holes are not just a singular solution of classical general relativity. From a quantum perspective, they are necessary for the UV completion of the theory in the Goldstone sense. Okay, so black holes are the objects that actually provide the scale of Planck mass in this perspective. And so, but the bottom line is I want to argue is that what you're doing is the entropy of these classical lump is not extensive. Okay, because if it's extensive, it will scale as a volume. It scales as an area. Okay? And so what the CGC is essentially doing is you have all this color, it's screening color completely within a distance scale, which is 1 over QS. Okay? So it's forming a colorless object on a very tiny scale, much smaller than the proton size, okay, so that all the information that's probed of this object is sitting on the surface. That's all you're going to uncover. And that's, so in that sense, it's very similar to the physics of black holes. And so what I want to argue further is that this object in QCD is a classical saddle point of the QCD effective action in the range of asymptotics, very high energies, only up to 1 over n corrections. Okay? So it's not a classical state. The CGC shockwave is not, it is a quantum object. It's not a stable object in time. And it's also a leaky condensate, and it decays on some time scale which you can calculate, which is 1 over QS times 1 over alpha.
Which n is this? The 1 over n correction?
This is occupancy. Okay, so it's alpha. So think of n as alpha s for this critical object. And so that's how we get this 1 over. So this is n over QS. 1 over QS. And QS, remember, 1 over QS is the size of this critical region of the classical lump. That's the size of a classical lump. Okay. So these classical lumps are much smaller than the size of a proton, okay, in range asymptotics. So the physics is entirely that of the microscopic objects of the theory, it's quarks and gluons, okay, but they are Goldstone modes in this picture, right, of a broken global symmetry. Okay, so there's a subtlety there. And so that Goldstone dynamics decays on some time scale. Okay, so there's a Goldstone decay time scale. And this is this time scale here beyond which time scale you can really think of this object as restoring somehow the full global symmetry of the theory. And then that's then eventually leads to quark-gluon plasma. So everything that I've said, if you read carefully this paper here, is implicit in this paper by Baron, Schiff, and Son, which is the bottom-up QGP thermalization scenario with asymptotics. So Gia and I have a conjecture, which is that both the CGC and black holes are semi-classical lumps, which have, in the sense that they also have maximum occupancy or definition of gluons or gravitons, respectively, which unitarize cross-section at some emergence scale. And in the QCD, this is a kind of black disk. It's a saturation scale, so it screens color completely. And then in the gravity side, this is the inverse of the Schwarzschild radius of the black hole. And at this unitarization point, the physics of the two is universal. You can map details of dynamics at this critical point only. Okay. When you go away from this point, where n equal to 1 over alpha, the physics is completely different. Apparently, I'm going to tell you it's more similar than what you would think, but they're different theories, right? What I'm saying is that at this critical point, you can really map. In fact, I learned a lot of black hole physics just through this. Okay, I mean, just by making the map in my head, then I would say, does this work? Yes, it does. You know, this is what it means. Okay, this is stage time. Okay, this is the decay of the condensate time.
So
all
the
this stuff.
Schwarzschild radius is 1 over QS on the QCD.
Yes.
So if I have your little pictures up
Right,
there,
right.
that colorful ones, it means I have lots of black holes in the circle.
No, remember, this is of size 1 over QS.
Oh, I thought
Yeah,
this is the size of the nucleus.
No, this is size 1 over QS.
But inside my nucleus, if
I can have many blobs.
I have lots of black holes.
Exactly. Exactly. Okay, so this is a frequent misunderstanding you find even with CGC experts. Okay, I mean, it really doesn't know about confinement in that sense. The confining dynamics is not related to the screening dynamics that I'm
No, I understand.
Okay.
It's just what I said.
There's additional non-trivial dynamics of confinement that comes in,
Yeah.
which tells you how these objects in radioasymptotics form the nucleon.
Yeah, understood. So, but in the nucleus
Right.
collision,
Right.
I produce lots of quote-unquote
Exactly,
black holes.
exactly. Right. And you can really think about this as these screen objects that are
Yeah.
scattering and then releasing color.
Yeah.
And the time scale over which they release this color is precisely the time scale of this bottom-up thermalization scenario. Right? Okay, so.
Raju,
Yeah, sorry.
maybe this is not a good question at all, but have you ever thought about the problem of collapsing stars, whether you get a supernova from it or a black hole? What are the conditions to reach a black hole given your formalism?
So that's a very good question. What I'm talking about is really, so when you think about the problem of black, say the collapse of a dust cloud, say a star, to a supernova, right? So you test, of course, there's degeneracy pressure, which would prevent, you have to reach a certain number of solar masses, and then of course the degeneracy pressure cannot fight that's a classical to classical transition. Okay? You're talking about an already formed classical object, right? Which is then collapsing to this black hole.
So you cannot derive then.
So I've already gone to the large N phase, and then I'm just talking about large N dynamics going on. Okay, I'm talking about how does this large N dynamics come about in the first place. So the analogy would be, what if you had a huge number of dust motes which are moving very close to each other and radiating gravitons of very small impact parameters? Okay, how do I form a primordial black hole? So it's not so much these particular kind of supernova explosions stuff that I'm talking about. So, but that's the underlying picture of how you would sort of get to such kind of. Okay, so I said that there's a universality of critically packed states, QCD and gravity, and I claim that universality is only at this unitarization scale. Okay, that I pointed out. I'm going to argue to you actually this correspondence may be deeper and more profound and can be extended even further. Okay? And that has to be something called the starts off with something called a BCJ double copy. So this is a huge subfield now. So that's work that was initiated by Byrne, Carrasco, and Johansson. And what they showed was that you could take perturbative QCD amplitudes, okay, and you could make a replacement of color factors with kinematic factors inside the calculation, and you would recover the gravitational amplitude. So they're looking at 4-point amplitudes, and they found that if you take these 4-point and 5-point amplitudes and you actually made these replacements, color factors and kinematic factors, and you get the results in gravity. Okay? And this has become a big field, and actually they're using this now, these techniques, to actually calculate the one-body potentials to high orders for black hole inspired dynamics. Okay.
Is this all in quench QCD, so no quarks? Or?
So this is really Yang-Mills, strictly speaking. So, and this follows from some work by Kawai, Liu, and Tai, where they showed, this really comes from the connection between closed strings and open strings in string theory, and it's the low energy limit of that, where you see that there's a correspondence between Einstein gravity and Yang-Mills. Okay. Where you can think about Einstein gravity kind of as a square of Yang-Mills. So the mantra is gravity is QCD squared. So this is no joke in the sense that they are actually able to compute to the highest order post-Minkowskian kind of in spiral dynamics using these techniques. So it's a very advanced. So there's a real emergent crosstalk between gravitational wave physicists and QCD physicists, and so-called amplitudes. Now, what I was talking about is how you go from perturbative QCD to QCD at high occupancy, right, to N, producing lots of soft gluons. And similarly, I was talking about gravity at high occupancy, which is black holes. The question is there now a direct double copy between QCD and gravity? And this is sometimes called the classical double copy. And that goes to this work here. In particular, is influenced by the work of Walter Goldberger and collaborators at and sort of related work.
So to which extent do you need QCD for this? I mean, I understand you need bosons, and you probably need some interactions. Why do I need a gauge theory? And if I need a gauge theory, does it have to be QCD?
So so this particular double copy is really between gluons and gravitons. Okay? And in fact, some of the
in SU2 theory, it wouldn't work.
So it's I think for Yang-Mills it would work.
It could work.
Yes. But so the details of the species dependence, in terms of quarks and so on. So some of the results are universal. They're independent of what the details say. So for example, if I'm looking at 5-point amplitude, in which I have two quarks and producing a gluon, there's regimes in which this physics is universal. It's independent of the fact that I had these particular flavor quarks. Right. And the same thing in gravity. If I had dilitons, scalars that are emitting the gravitons, that would also be the case. So what I'm going to talk about now is how do you go from amplitudes, right, completing Feynman diagrams, S matrices, to looking at shockwaves. Okay, how does one go from one to the other? So now I'm going to discuss, the structure of two amplitudes. Okay, so think about two objects, right? You can think of them as quarks, which emit n gluons. And this is the most favored process because gluons like to emit more gluons. So if you have two quarks exchanging gluons, it's more favorable to emit a gluon, say, than a pair of quarks, quark-anti-quark pairs. And in fact, that's especially true in this multi-Ray J asymptotics, which corresponds to an ordering in how fast or slow these gluons are. Okay, so think about, say, this guy as being the fastest object, and then this gluon is being a little less fast. This is slower, slower, slower. So they order in rapidity. Okay, so in speed. So the fastest gluon is going this way, depending on the frame, of course. But pick a frame where this guy is the fastest, and then everything else is ordered relative to it. Okay, and this is sometimes called multi-Ray J kinematics. So the rapidities are ordered along this ladder. And that turns out to be the dominant contribution, okay, in the true sense of asymptotics, according to Wikipedia, right, of what dominates such cross sections. This is a microscopic calculation. What I talked about earlier, 2 to n, that was general consideration. This is a specific QCD calculation. And this goes under the name the BFKL ladder, after the people who came up with it. Okay? And this is the leading contribution for turbulent QCD at high energies. Okay? And so these partons that are produced is called so-called weak partons. They're slow compared to the other counterparts higher up in the ladder. And this is sometimes called the Regge regime of QCD. And you can describe this process in terms of a renormalization kind of picture where things one rung of the ladder influence the next rung and so on. So you don't necessarily have to compute the whole ladder, you just know the dynamics. One rung, it goes down. Okay. And that tells you how cross sections grow. Okay, so this is the amplitude in terms of the Mandelstam invariance, the central mass energy and the momentum transfer squared. And that goes as S to some alpha of t. That's where Regge comes from, right? So this is what we learned from Regge theory, that the cross sections,
Touch it again.
A touch.
We're squeezing with your
Wow.
fingers.
Oh.
Actually, I was about to suggest maybe it would be good to expand it and center it a little.
Oh, I'm sorry. Is it too small to read?
It's a little sense at the top and bottom there.
Good. That's great. Wow. So this is what Regge tells you is that cross sections go with some power of some function alpha of t. So this is where t is Mandelstam. So this is the Pomeron intercept, if you like. So if it's a region, this would be the region intercept, right? And then this is the string tension. So alpha prime is the inverse, so the inverse of that is the string tension, right? So this is really stringy dynamics that comes out in Regge. And so the growth of the cross section is described as something called the BFKL Pomeron. It's a color singlet exchange, right? Which is a ladder of color singlet exchanged gluons. So the imaginary part of that amplitude is what gives you the total cross section, grows with energy, okay. All that good stuff.
Roger, naive question.
Yeah.
My understanding rigid asymptotic or whatever it's about is really trying about looking for 2x2 process.
It's imaginary part of this is a 2x2 process.
Yeah. So the question concern is not really 2 to n, but it's 2x2.
Yeah, but at high energies, right? That includes the cross section, right? It includes all possible ends.
Yeah. So I understand. For example, it's a 2x2 process. You're talking about region exchange and so on.
Right.
Or you can understand the total cross section for 2x2 process like that.
Right.
And under the assumption that you integrate all the phase space of the
Right.
region.
Exactly.
But you're not particularly described 2 to n.
So no, but if I think about very high energies, right? And I'm looking at the 2 to 2 scattering,
yeah,
right? And then this corresponds to a cut,
yes,
right? And if I cut that diagram, if I take the imaginary part of the diagram, right, that's a 2 to n.
I know but it may not be a 2 to n dominant source for 2 to n. So in a sense, your ridge behavior is really for the 2 to 2. It's not really for the 2 to n.
Oh, I see what you're saying. Yes, of course. I'm talking specifically about the 2 to 2 amplitude and taking the imaginary part of that, the total cross section. Very good. Yeah. Sorry. Yeah.
Well, okay, I was confused by something. Is that if I grab a 2 to 2 amplitude, arbitrary energy, I cut that, then I get the sum over all possible intermediate states.
Yes.
So it's not like n is a.
No. But
Okay.
it's the same way you would go ahead and then compute the 2 to n process as well. I don't have to integrate over all of these states. I mean, what I'm saying is I can. So this calculation is I can actually compute the cross section to produce n guys. I can integrate over the phase space, right? And then that's going to give me the total cross section, right? Or I could just take the imaginary part of the 2 to 2, right? But to actually compute this the other way, first way, I have to actually compute the amplitude of 2 to n, then integrate over phase space. So in that process, I have computed the 2 to n amplitude. I'm happy to. No, right? It's taking m squared, right? For 2 to n, integrate over all n, right? That gives me the total cross section, right? Or I can just take the imaginary part of the 2 to 2 amplitude that they agree, right? That's the optical theory. So what I just said is optical. But if I don't integrate over the phase space, then that's the point that's I think fun. That doesn't have the structure. It has a much more complicated because you're sensitive to detail kinematics. Now, in this diagram here, so please slow me down if I'm going too fast. These objects actually in high energies are not gluons. Okay, that's why I have them in black. And these red blobs are not just the simple gluon vortex. Okay, they're more complicated objects. And what it is, that red blob here is the sum of all 2 to 3 diagrams. So imagine I have a 2 to n ladder and I broke it up into blocks. Okay, sorry, into little subsections, okay, which contain all 2 to 3 kind of processes where I produce gluon. And so now, so if I go back here, what I mean is that I'm breaking it up into one such thing. I'm breaking it into one such thing here, second, and so on. Okay, so I'm looking at each sub-blob, sub-ladder, and then what that sub-ladder is, right, which is corresponding to this, corresponds to summing all possible ways I can produce a gluon, right? I can produce it from the top, I can produce it from the center, sort of in the middle. I can produce from all the different legs. I sum all those up, and when I sum all those up, it turns out I can write it as one effective diagram, and that's where the ladder structure comes in. Okay, because you just take all the possible Feynman diagrams, right? Where do you get this nice ladder picture, right? It's because these guys are effective vertices, and that's what's called a Lipatov vortex. It's a momentum-dependent vortex, and it has this kind of kinematic structure here. Ignore it if you don't care. The important thing is that this is gauge covariant. Okay, so the square is gauge invariant. Now, this other thing that I showed, which is exchange in the T channel, this solid blob here, the solid, gluon line, is actually not a gluon, but it's a sum of all possible virtual emissions to all orders of perturbation theory, including all such contributions. And what that does is this exchange is not just the T channel 1 over propagator, T, okay? It's 1 over T times e to the alpha times this difference in rapidities between one leg of the ladder and the other, and the next one, right? And this alpha of T is this object here, and this is essentially what is the pseudocount double log. Okay, so this is a log, is y minus this log of energy between one rung of the ladder and the next, and this also gives me a log. Okay, this is an infrared divergent object. It gives me a log, so I get this double log. Okay? And so essentially, you're dressing the gluons. Okay, this is a dressed gluon, and that's your regio. Okay, so this object is a regio, okay, because it has the structure of a propagator, which is given by this alpha T. And so when you include all of these, regioized gluons and combine them into the 2 to n scattering, right? That's how you get the Pomeroy, which is a color singlet combination of 2 regions. Now, so this is the BFKL equation, and you say, well, okay, what is this? What is the BFKL amplitude? So if you look at the forward scattering amplitude, and it turns out that it's actually sick. Okay, that when you solve this, very complicated equation, including this 2 to n scattering. So if you start with some initial distribution where all emitter gluons have some, some momentum, right, which is concentrated in a perturbative regime here. So you're looking at hard emissions. When you solve the equations and you look at high energies, it turns out that there's a diffusion of this physics to the infrared. Okay, so physics goes over to lambda QCD scales. So this perturbative construction breaks down. Okay, and in fact, this is a breakdown of the operator product expansion. So there's a very nice description of this paper by Balmuller. And so now, if you actually try to go to next order, so include further loops and so on in this ladder, it doesn't cure it. Okay, so when you go to next to leading log accuracy, that's next order in this kind of ladder construction, it doesn't cure this diffusion. It's always there. And the only way it would be cured is this phenomenon of gluon saturation. You get maximal occupancy, right? And that can be thought of as, all in the language of OPE, as what I mean by OPE breaking down is that you get all twist contributions in the language of operator per expansion, which are of order 1. Okay? And that happens precisely when the occupancy is of order 1. So this is a different way, coming from perturbation theory, of realizing this concept that I was telling you in the language of information theory, that you saturate the vacancy bound. That was a very general argument, right? This is a very micro argument, okay? And they both lead to the same conclusion. That what cures infrared diffusion is a classicalization of the process, which also happens in the cross-section unitarizes. And okay, so that's coming back to this picture here. And it turns out the microscopic calculations actually, they give you a variation of this BFKL equation, okay? And that's a very powerful RG picture, which includes all kinds of nonlinear contributions corresponding to higher twists, and they have a non-trivial fixed point. And that non-trivial fixed point is really what generates this unitarization boundary. So this is coming at it from this side, as opposed to sort of these information theoretic arguments. Okay. And so what we call gluon saturation is the emergence of a non-trivial fixed point in a renormalization group evolution, which generates this scale, this saturation scale. So it's not something you put in the hand, it's something that's emergent. And it's a large scale. Okay? It's a much larger scale than lambda QCD, radio asymptotic, so all the physics is really governed by the dynamics of this scale. And so that's what, so this is, so think of a deep elastic scattering, say the EIC, or maybe super EIC, we don't know, we'll see. So imagine you have a nucleus with A nucleons, right? And these valence quarks are moving very fast, right? And then there are slower guys which are kind of lagging along, but which are coherent with the nucleus. And if I look at it at very short distance scales, this is the classical blob that this probe sees, okay? And the exchange of this guy is precisely a radialized gluon. So this is not a gluon. So what this is doing is it's forming a classical field, an emergent classical field, and what it's exchanging is this radialized gluon, which is the scattering of this. Am I doing crazy bad on time?
How long do you think you've taken?
Yeah. What's that?
How long do you think you've taken?
I don't know, 10 minutes?
10 minutes left.
Okay. Okay. I can stop anytime. Okay. So, but I would miss the punchline. Okay. So, so what I'm saying. Okay. So remember, I'm talking about a 2-to-n process, right? But then what I'm arguing to you is that this very complicated 2-to-n process, right? Two gluons get n gluons, can really be thought of as a scattering of two classical blobs. Okay. Because if I'm interested in the physics of something going on at central rapidities, right, which is this guy here, this is in rapidity space, okay, fast guys this way, slower guys towards the center. So from the point of view of this guy here, all of these guys look like one coherent classical blob. Okay. So it's, the wavelength is probing, this is some, and you can think of it as some classical color charge density. Okay, so it's a higher dimensional representation. So I'm multiplying, T's, right? Different color factors, get a higher dimensional representation. Okay. And that's a classical representation, right? The color charges commute. There's a large n limit. And so these are two classical color charge densities that are scattering and they produce this. So you turn a very complicated amplitude calculation into a classical Yang-Mills calculation, right? Where you have two classical blobs that are scattering, producing a gluon. And this satisfies an RG picture. So if I'm looking at the next rapidity, I know how to calculate, through the next rapidity and so on. And so this is kind of basically calculation where I'm computing collision of two shock waves. Okay? Now, there are different approximations where you can have analytical results. And so the only scales here are the classical color charge density characterized by a QS of this blob here, the QS of this blob here. And then you can work in an approximation where the momentum transfers are large are small compared to this characteristic dimension full scale here. And that would be the color charge density divided by KT squared. So if these are very dilute, then you can really analytically calculate this cross section here by solving Yang-Mills perturbatively. You can also do the same thing if one of them is dense. So if the other is having multiple exchanges, which are all of order 1, right? So the density of this guy divided by so it's a very dense object here divided by KT of the exchange is of order 1, then you have to include all such coherent radii scatterings. And we can also do that analytically. It's only the case when you have both ends, like in a nucleus-nucleus collision, that you have to do things numerically. And so basically the problem is shockwave collision. You have two colored currents, right, which are delta functions. They're shockwaves at very high energies, right? These are fast along the light cone, ultra-relativistic energies, right? So you have two shockwaves with delta functions, x minus x plus, collide, they produce radiation. That's your quark-gluon plasma. Now, as I said, in the simple examples of very high KTs relative to the color charge density, you can write the solution for what the gluon distribution is. And that can that's what we found was this is the same Lipatov vertex that I mentioned is all the stupid 3 Feynman amplitude calculations. Some you can do it from a classical calculation. So you've recovered this classical calculation. And then this can be written as the product of the color charge densities divided by the typical momentum transfer squared. That's this Q2 here, right? And there's a Q1 from the other side. And in the dilute dense, you can write this in terms of something called the Wilson line, which resums all these coherent multiple scatterings. Okay, that's the phase. And that phase depends on this color charge density divided by KT squared. And this object, these objects are what are the radii. Okay, so this is what gives you, as I argued, it gives you quark-gluon plasma formation, and then these things are that dense. If you're interested in the details, you can look at our RMP. It leads to thermalization. You can actually compute the thermalization temperature and time. It only depends on the scale QS, okay, in asymptotics. It's really incredible, right? Incredibly complicated objects collide. And radii asymptotics, you can describe the thermalization temperature and the time it takes to thermalize in terms of one scale. And in the limit where QS goes to infinity, thermalization is almost instantaneous. Is that shocking? Or? So in some sense, it's not very surprising that if you have very high multiplicities in very small systems, you can have thermalization. You know, it only depends on the saturation scale. So as you go to higher and higher energies, the saturation scale becomes bigger and bigger. Okay, and so everything is just governed by that scale. And so the thermalization time gets smaller and smaller. It gets almost instantaneous.
Seems intuitive to me. I mean, why should I be shocked?
You shouldn't be. But people are, right? When you say, oh, the small, PP collisions, so on, organization. But it's as you go to very, very high energy. So this is all in asymptotics, right? Now, if you're a hard-nosed person, as I know you are, you can say, well, what is this coefficient here? And that gets to be very challenging. But just parametrically, this is kind of the answer. And so what I'm saying is that the other thing you should be shocked by is I'm talking about completely perturbative physics, right? I'm talking about weak coupling, but I'm getting thermalization. And the reason is because the occupancy is very large. So
thermalization on what scale of the scale QS? So how big is my thermalized system? Is it the whole nucleus?
Think of a proton, it's the size of, so even in PP collisions, right? If QS, right? If one over QS is much smaller than the radius of the proton, I would get thermalization.
Wait. So you told me the QS is the size of my black hole.
Yes.
So is the black hole thermalized, or is the whole ensemble of black holes which I have in my nucleus?
This answer is for the ensemble.
How do I see that?
Well, this is this whole bottom-up picture because this is a whole complicated process it goes through. You have to trust me on that or read this paper, but that's.
I know this paper.
Yeah. The coefficients of this are hard to compute. Okay, so that's where the real challenge is. But it leads to kinetic theory in sort of the late stages. But there's a very non-trivial process that goes on.
So eventually, I mean, the reality of the hard-nosed questions come into play.
Yeah.
So,
Sure.
Nothing to say about this theoretically,
Right,
does it have some phenomenological relevance to
Of
the
course.
LHC?
Oh, of course. I mean, first of all, I would say that the scale that controls the reason why event generators work is really this QS scale. I mean, they're all inbuilt into every event generator, from EPOS to Pythia. They all have this color screening scale. They, of course, you put it in some kind of by hand, okay, but without such a large scale, none of them would work.
I think people have intuited this phenomenologically for
Yes.
basically since
Yes,
birth of QCD,
because
and now you're putting it on a formal basis?
yes, yeah. Well, I'm saying why, because you see that the mini-jet cross sections diverge, and the place where they diverge increases with the energy, the PT, right? So why is that happening, right? This is telling you kind of the.
When you say mini-jet cross-section diverges, I mean this energy momentum conservation, so it cannot diverge.
Of course, but why should it diverge at 3 GeV as opposed to lambda QCD?
Oh, it can, you
So
got an infinite
QCD
number of infinitely soft guys.
Non-perturbable QCD would tell you, well, of course, there's no violation of unitarity, everything's sort of screened at lambda QCD, right? If you put that scale in, you'll be totally off. Okay, this is not going to happen. So basically what I'm trying to argue to you is that exactly the same thing happens in gravity. And this is a remarkable thing, is that the gravitational Lipatov vortex can be expressed as a bilinear of the QCD one. It's a double copy of a 2 to 3 vector vortex minus that of the QED one. And this is an absolutely remarkable result that was discovered in 1982 by Lev Lipatov. It was discovered well before, 40 years ago. Discovered well before this famous BCJ double copy. And there's a non-trivial reason why the QED branch vortex enters in, and I won't go into that here for lack of time. But we have a nice physical understanding of why that happens. So basically, I can do the same problem of 2n amplitudes in terms of shockwave collisions in gravity. Okay. And that in gravity goes in the name of the Aschenberg-Zexel shockwave metric. And what it is it has a structure here, where this F is basically this scale that I introduced in the QCD case, which is the density. Now here, it's not color charged, just the actual density of gravitons divided by kT squared. And that can be written, in terms of this Coulomb kind of relation here, right? Poisson equation. And this is the actual Zexel shockwave metric is a solution of Einstein's equations, which is sourced by the energy momentum tensor of a shockwave. This is a shockwave, okay, with this mass density here. And in thinking about the shockwave collisions, I have to think about the mass, so the energy in such a way of being fixed, where m goes to 0 and gamma goes to infinity. That's the limit in which one develops the Aschenberg-Zexel shockwave metric. And so if you linearize around this metric, so imagine you have a shockwave that's coming in, that's this guy here. Okay. So you do sort of linearization around this metric. Think of this as a gauge field. Okay. So you're linearizing, and this is the proportional Newton's constant. And so this h mu nu is the fluctuations, and that satisfies, it gets rotated, okay, if you like. And this is the gravitational Wilson line. Okay. So in QCD, this would correspond to a color rotation of a gluon. It's coming in around this object that's scattering. While in gravity, this is just a metric, right, times a shift operator. Okay. And that's what explains the Shapiro time delay. It is in gravity, this thing is kind of shifted by a little bit in scattering. And you can see there's a map, right? If you take the gauge field, replace it by the metric, or you replace the color factor, which appears in QCD with this shift, you recover the same result. And this is a powerful thing. So in gravity, you can actually compute a scattering where now includes all these soft graviton exchanges in these guys here. Sorry. So you can actually go through this whole calculation. Okay, you're solving Einstein's equations, okay, for shockwave collisions, and voila, you recovered as a result. Okay, which is where this is now the gravitational Lipatov vortex, okay, which was a double copy of the QCD. Exactly what Lipatov showed. You were able to show that it's actually the double copy of the QCD. So you see the exactly analogous structure, okay, except there's now color factors are not there, right? But this has this double copy of this object here times the QED, Ramshaw vortex. Okay, so this is kind of a very striking result. It's discussed in detail in a paper. We do the actual gravity calculation in great detail. Now, I'm ending here. So I'm actually going to finish just 2 minutes, okay? So now, remember I said this is universality, okay, which is coming right at the unitization. Now I'm claiming that this is even more general, okay? So this is actually from a paper by Goldberg and Ridgway, where they showed that if you just computed this 2 to 3 QCD amplitude in general kinematics, okay, not in the high energy limit, and then it turns out that there is a powerful double copy to gravity amplitudes, okay, which include many, many more diagrams. And what you do is you solve something called Yang-Mills plus Wong equations. And Wong equations describe, so think of classical color charges scattering in some background field, okay, which is slowly varying. And you can look for radiation in that background field, okay, and you can compute what that radiation spectrum is. Okay? And this is the result. Okay, so it has a term which is, these are the color charge densities, the C's, they're color labels, and it has a structure factor here. But then there's also this additional term here, which is the dot product of the color charge densities. Okay? And this is some phase space factor here, okay, this mu. Now, when you take the ultra-relativistic limit of this result, you can show this recovers precisely the result I showed you earlier. Okay, this is the Lipatov vortex. These are color charge densities. This is a structure factor, and this is characteristic 1 over Q1 squared, Q2 squared of the exchange gravitons. Now, if you now make the following replacement, replace the color charge densities by momentum, replace the color factor by some product. So this is like a 2 to 3 vertex, except this only contains momenta. Okay, no color. So you replace color by kinematics. Okay, and you replace the QCD coupling with the gravitation. You recover precisely the result that I got from explicit gravity calculation. So what this tells you is that, amazingly, right, the collision of gravitational shock waves, very high energies, okay, knows about this double copy to the collision of gluon shock waves by this very replacement. In principle, you can use this to compute the gravitational wave spectrum in high energy dynamics. And by the way, our work is very similar to that of Veneziano and collaborators, which I failed to mention. So if you read our papers, you see that we discuss their work extensively. And we can actually compute the Weizsäcker-Williams spectrum in gravity. Okay, so if you think about shockwave collisions, these are QCD. So think in QED, you have boosted charge, the Weizsäcker-Williams distribution, right? And in QCD, there's an analogous Weizsäcker-Williams distribution. Turns out there's some with one gravity too, which is analogous. It has a different shape from the QCD case, okay, but one can calculate it, and this is also discussed in these papers here. As a next step, we can compute shockwave propagators in gravity using our same strong field techniques as in QCD. And then the holy grail is whether we can solve the RG equation in gravity, use exactly the same way we did in QCD, okay, and discover a non-trivial fixed point as a critical impact parameter. That would be a black hole. So that would be the microscopic derivation of the black hole, right, as a non-trivial fixed point of 2 to n evolution in gravity. And so that's my last slide. Thank you very much. Sorry, I went a little bit over. But not too bad, right? The statute of limitations.
A stupid question.
Yeah.
I thought that the gravity is not quantumless, so there's always a problem in how you quantize gravity, right?
So, very good question. So gravity at one loop is renormalizable. And what we are talking about, there's a question online. What we're talking about is really an iteration of one loop. So Thorsten Weltman, a very beautiful paper, showed that gravity of one loop is renormalizable. It's really two loops that really becomes a problem. Okay. So the practical answer to your question is that what we're looking at is an iteration of one loop amplitudes. Okay. So if you wanted to do the analog of next to leading log in gravity, then it would be possibly problematic. But in gravity, remember, alpha gravity is very, very small. Okay, so those corrections are highly suppressed. So there's another answer to your question, which is more non-trivial, okay? Which is that what Lipatov showed is that the non-trivial answer is that the problems are with renormalization are in the UV, right? The UV in gravity, it's short distance. You have formation of black holes. So unlike QCD, where color screening is happening in the IR, in gravity, right, black hole formation is occurring in UV. So if black holes UV complete gravity, that sets a scale for your UV divergences. So to the best of my knowledge, right, no one has done the calculation, right, of doing higher loop contributions in strong backgrounds in gravity. In QCD, it's irrelevant because the UV is the weak field limit. So the fact that it's a shockwave, you don't care. Okay? The background field doesn't matter, right? The UV dynamics is universal. That's not the case necessarily in gravity. Okay? So that would be a highly non-trivial way to proceed.
Okay.
There's a question online.
Tony, please.
Yeah, so I have this duality is true only for 3 colors, or it's true for any number of colors?
Oh, as I said, no, it's valid for any number.
Okay, and
I mean, I'm talking here specifically with SU3.
okay, thank you. And also, so what's the shortcoming of this compared with ADS-CFT? Is there any? This is not fully tested, verified. This is a really duality between true gravity. So what's the shortcoming disadvantage compared with ADS-CFT? So because this one is not fully verified for all correlation function.
Okay, very, very good. Thank you. Because this is a question someone else asked about ADS-CFT. So what people have done is they've studied what they've done so far. So, and let me also address your question further. Is that in ADS-CFT, what they do is in the QCD, so it's a correspondence, right, in ADS between correlators in n equal to 4 Yang-Mills and gravity net de Sitter in 5 cross 5 dimensions, right? When they do these calculations, what they do is they are actually not colliding actual shock waves in gravity. Okay? So the QCD analog, when they're thinking about the QCD collision, right, of gluons with the stress tensor, the delta functions. In the gravity side, the calculation they're performing is not an actual versus axial shock wave in gravity. They just have a cosmological constant. And that cosmological constant is the analog in ADS of actually thinking in their language in terms of shockwave collisions in gravity. So the gravity calculation is not a genuine shockwave calculation. It's a much simpler calculation in some sense. And what we are talking about is real shockwave collisions in gravity. And this was actually done a long time ago by Kip Thorne and collaborators, Thorne and Kovacs, and also by Ethan Payne. There's a whole literature of this stuff. What we are actually, so ours is actually really a different construction, right? We're interested sort of in the quantum features of this process. So that's kind of where we're going. Now, your second part of your question was about correlation functions. And so that's actually where we want to go. Is our whole idea is to compute shockwave propagators. So those are 2-point functions. And we want to check whether there's a similar kind of double copy in terms of the shockwave propagators in our QCD picture and the gravity picture. Now, whether endpoint correlations, that's a different question here. But I think I'll be happy just with 2-point correlators.
Maybe I'm missing something about the big picture. I mean, it sounds like at this point you guys, although you don't have a general proof, you're just making these observations. So there's a correlation between the QCD side and the gravity side. But ultimately, you have to do both calculations and check the correspondence. What is it that you're seeing? What is it that is going to eventually bias that you can't do?
Very good, very good. So the first part of the talk, right? I was talking about a QCD calculation of shockwaves, right? And I was talking about a gravity calculation of shockwaves. So these are honestly done calculations both in QCD and in gravity, using actual shockwave calculations in both cases. And then we saw that there was this double copy. Okay, so that was really from explicit calculations. The second part of the talk, this last part that I talked about, was basically seeing that I could have just taken a variant of this QCD calculation, right, in exact kinematics. We were working in shockwave kinematics in both cases. We could have taken just a simple QCD calculation and then made this double copy replacement, and then we would recover the answer that we had in gravity. Okay, so it's telling you there's something deep about this kind of double copy relation that was discovered by Goldstone and Ridgway. Now, the more non-trivial question then is, okay, this was also, I think, the subtext of the question that was asked, is does this persist then for higher order correlators? And really, strictly speaking, the only way to check it is you do the calculation in gravity, you do it in QCD, compute shockwave propagators, see that if this works, and where does it start breaking down? So it's no guarantee that this will work to all orders, and so on. So it's something that, it's a nice thing, right? And its power can only be tested by explicit demonstration. There's no deeper fundamental reason, right, in the structure of the theories necessarily, as far as I know. Maybe some speculations based on twisted theory and so on, but there's no real absolute first principles claim that this should be a generic feature. It's something that it's an observation, right? And it's a powerful observation. It's not a trivial one. And so now we have to see how far.
You would go as far as that correspondence should be common among any gauge theories, family of gauge theories?
So no, I am very skeptical of that. I think this is really, so there are some universal, so the quantum vortices in gravity are universal. They don't care about, whether the gravitons are coupled to some different forms of matter. Okay, so it's the leading contribution that's universal. I don't believe it's true for any kinds of matter, for example, if you go further to higher orders and so on. So it's something that really we have to understand better. It's kind of the first step.
Okay, maybe we should.
Interesting.
Maybe we can discuss offline later. Okay, maybe thanks for your again.
Thank you.